right. Hello, everyone, and welcome to this week's Digital Manufacturing Talk. My name is Tyler Fenhouse. I'm the marketing manager for Symphony AI Industrial, and we've got a great informational talk lined up for you today titled Accelerating Furnace Performance with AI. As you may know, Symphony AI Industrial is a leader in industrial AI solutions in digital manufacturing, plant performance optimization, and connected worker. Symphony AI Industrial is a Symphony AI vertical. There are several Symphony AI verticals there on your screen, and we are one of the largest, if not the largest, enterprise AI companies with more than 1,600 customers and 3,000 employees. We are presenting on the Teams format, and we will have a couple of poll questions, so make sure you're on the lookout for those. And if you have any questions for our presenter today, Prashant, he will answer them here live at the end of the presentation. So make sure you're typing those there in the chat as we go along. All right, Prashant's got a lot to cover, so I'm going to hand it off to him, and we're going to get this talk started. Prashant, take it away.
Yeah, great. Thank you, Tyler, and good morning, good evening, everyone. My name is Prashant, and I'm the Director of AI Products and Applications at Symphony Industrial AI. Have a background in controls, optimization, data science, AI, ML, and been with Symphony for around 5 years. So today, I'm going to be covering the following topics. So I will give an overview of melting furnaces and talk a little bit about the application. Then I'll get into the details of how we built our AI ML modeling framework and how we build these digital twin models, deploy them, and show you some results. And then finally, I will give a quick demo of our Furnace digital twin application, and then talk about some next steps and a summary of what we've accomplished. So before we get started, we have a poll question, so I'll hand over to Tyler for an opening poll question.
All right, so you should have your, the poll question should pop up there in front of your screen, just real basic, try to get in a feel for the room. How much AI and automation do you use for furnace operation? A lot, or it could do better? So pretty simple there, but again, Prashant just wants to get a feel for the room before we move forward here. So go ahead and get those polls in, and we will go ahead and move forward. Looks like about majority of the room is voted. 82% can do better, and I assume that's why you're here. But if you haven't voted yet, please get those polls in. All right. So Prashant, it looks like 18% they do a lot of automation, and 82% of the room can do better. Back to you.
Okay, awesome. No, thank you. Thanks to the audience. Thanks, Tyler. So I hope you can get something useful out of this, and I can give you a flavor of how we offer our solutions for melting furnaces. So we'll start with an overview here. Just very broadly speaking, a melting furnace is an industrial appliance that is capable of heating materials, and these could be metals or glass or silicon metals, to elevated temperature that is above their melting point, so that they become liquefied and molten and also homogenized. And usually the need for this is to basically cast raw materials and then melt them and then come up with a product, after cooling, so that that product meets certain quality specs and requirements of very specific applications, right? Some of the common types of furnace, there are various ways of classifying it, but a common way is through the energy source. So you have electric arc furnaces, you could have oxy fuel fired furnaces, you have induction furnaces, and there's different types of furnaces in the industry. Some of the concepts that we will talk about here apply also to the so-called smelting process. So this is beyond just increasing the temperature and melting the material, but it also involves a reduction of an ore into the pure metal, right? As we elevate the raw material to high temperatures. And good example of this is blast furnaces, where we extract iron from its ore. Likewise, aluminum smelting processes. So today we will focus mainly on glass smelting furnaces, but a lot of these concepts that we will talk about apply very broadly, because we're really looking at how do you predict the temperature in the furnace, and how do you achieve homogeneous temperatures? How do you control the furnace so that you get a good quality product? Okay, so if we turn our focus specifically to glass manufacturing, this is a schematic of a typical glass manufacturing process. It starts off with raw materials, which is primarily silica, roughly 60 to 70%. You also have soda, limestone. Cullet is basically recycled glass, and also some colorants and other agents in small quantities. And all these raw materials are mixed in the right proportion in a metered batch. And then they're sent into a batch house, and then they enter the melting furnace from there, where the temperatures are elevated and maintained at close to maybe 1400 to 1500 degrees C. Once it goes through the melting, then it comes out into a conditioning and forming unit called 4 Hertz. And then it finally comes out of a mold, right? So the molten glass comes out, and then it takes the shape of the final product, which could be actually a bottle, but it could also be fiberglass or sheet glass, right? And then you finally have an annealing process where there is a very controlled cooling that happens. And this is mainly done to make sure that the glass is not very brittle. And finally, it goes out into quality control and packaging. You have a lot of automatic inspection, but also manual QA checks before it goes out and the product is packaged and shipped to the customer. So one fact here is that the melting process is the most energy intensive process. It consumes roughly 70 to 80% of the total energy consumption in this glass manufacturing process. So if you're looking at energy efficiency, you would focus mainly on the melting because you can get more gains from improving the energy efficiency of the melting process. Okay, now the furnaces can also be classified as per the way the heat is recovered from the flue gases. So most of the furnaces in the world today are actually gas-fired or oil-fired. So the regenerative type of furnace, basically what it does is it recovers the exhaust heat through these checkered bricks. So you would have a cycling of inlet and exhaust gases. The exhaust gases heat the regenerator bricks, and then the intake gas absorbs the heat from those bricks, and then you recover the energy that is lost in the exhaust gas. You can have different variants here. You could have an end-fired or a side port fired or cross-fired, depending on the arrangement of the fuel nozzles. But this is really the most popular type of furnace today in the industry. So you will see that a large proportion of furnaces are regenerative type. The other type is recuperative, and the difference here is that you have a dedicated heat exchanger called a recuperator for exchanging the heat between the cool inlet gas and from the exhaust gases. The main difference here is that you don't have a mixing of the inlet and exhaust gases. So this is used in very niche applications where you don't want to contaminate the inlet air and the glass, right? And these are used for smaller scale furnaces and not as common as regenerative. So yeah, this is one type of classification. And you also have the all electric type of furnace where you don't have any fossil fuel combustion happening. So obviously these are very clean and you don't have the problem of emissions. So they are becoming more popular. However, they are much more costly, both in terms of the capital investment and also in terms of maintenance of these electrodes. So they're still being used only at relatively smaller scales. But you do have a lot of furnaces that have a hybrid configuration where you have gas-fired combustion and also some electric boosting at the bottom to maintain more homogeneous temperatures and use a combination of sources. So in terms of the applications, now there are many applications for glass manufacturing. These are some of the key applications. So container glass is obviously very popular because glass is still a very commonly used material for both in the food and beverage industry as well as in the pharma industry. And then, of course, you have fiberglass. Fiberglass is used a lot in composites or in as construction material, mainly because of the good properties that it has in terms of the strength to weight ratio. And the third one is float glass or sheet glass. And this is used, for example, in LCD panels or mobile phones as the glass substrate, as well as in solar applications on solar panels, just as a protection layer, and also in buildings and automotive industry. So these are different types of applications, but the basic furnace that is used for manufacturing glass, the concepts remain the same, but you have a difference in the production side. And you also have very unique challenges in each of these applications. So in the case of fiberglass, you have a problem of fiber breakage. In the manufacturing side, you need to control the number of fiber breaks. And in container glass, of course, what we see is that this presence of seeds and other defects in the glass sometimes is not tolerated. And also, these type of furnaces also manufacture a different variety of products, and there are a lot of throughput changes that disturb the equilibrium in the furnace. And finally, in float glass or sheet glass, for example, in the LCD panel manufacturing, the customers are very sensitive to small defects like bubbles in the glass. So there's often very stringent quality requirements here, and the need to maintain a very uniform surface with a low variation in the thickness and also the strain. So now when it comes to glass furnace operation, what are the main KPIs that would be of interest, right, for an operations engineer or operations manager to focus on? So the first one is specific fuel energy consumption. So this is obviously very important given the energy intensive nature of the process. And this is defined as the energy consumed per ton of glass melted. The second one is the throughput or the glass draw, which is the tons per day of glass produced. And this is obviously important in terms of the production from the furnace, because you want to achieve certain production targets and maximize the throughput from a given furnace design. So this is obviously important. Then furnace health is important because these furnaces degrade over time because it's very high temperature operation. So it becomes important to monitor the refractory health of the furnace and how it's degrading. Then glass quality is important, obviously, from an end customer standpoint in terms of acceptance. And there can be many KPIs to measure glass quality. For example, the seed count, the count of bubbles, as well as other kind of defects that may be monitored. And the glass quality parameters can be measured either through automatic optical inspection machines, which are very common today. But you also have a lot of manual measurements in the lab because of limitations in these machines. But you do see a lot of AI-based inspection systems also today that are coming into the market, for defect identification and measurements of defects. And finally, you have the emissions, which is, of course, very important in many parts of the world. And this is, again, a very energy intensive and hence emissions intensive process. So you do have significant amount of CO2 and NOx, and there is a lot of focus on minimizing these emissions. And hence you have, oxy fuel fired furnaces and also the electric furnaces that are coming into the picture. So obviously emissions is an important KPI that needs to be monitored from an environmental standpoint. Now, what are the challenges in glass furnace operations? So this is really a very complex and intriguing process because there are a lot of uncertainties in the melting process, and it's a very complex combustion process, and also there's a lot of different sources of heat transfer and heat loss. And that makes it's a 3D kind of heat transfer and fluid transfer process. So it is very complex to model. And you have long time scales for the melting, which again makes controls quite challenging. So you have 24 to 40 hours residence time of the glass in the furnace from the time it is fed in as batch to the time it goes out to the product. So obviously you're talking about controls with a long time delay and time lag, which is always challenging in terms of stability. Then you have a lot of variability in the parameters like the glass throughput. In certain applications, you do have a switching of products and frequent changes in throughput. You also have variability in the gas calorific value depending on the source of gas or fuel, and you also have variations in the batch composition. Then you also have degradation of the furnace over life. So these furnaces typically tend to degrade. There is refractory degradation. You have deposits building up on the furnace walls, and you also have other sources of degradation. So this is something that you always have to deal with, and this also changes to some extent the heat transfer properties and the behavior of the furnace over time, and the efficiency as well degrades. Then the glass quality prediction is always challenging because these lab measurements are very sparse. Usually they're done once in a shift or once a day. So you don't get online or continuous quality measurements for all the quality parameters. And that sometimes makes it challenging because you have a long time between the time when you are able to see a change in your quality or a degradation in quality and then react. There can be a long time lag. And finally, sensor failures and drifts are very common in this application just because of the high temperatures involved. You have thermocouples fail, and then that makes it challenging to get an accurate picture of the temperature. So there are other ways of measuring temperature like optical pyrometers and thermal cameras and so on, but the standard thermocouples are always susceptible to failures in these harsh environments. Now, taking a thermodynamic view of a glass furnace, so this is showing you the energy flow process. And you have, of course, the cool air coming in, which extracts some heat through the regenerator or recuperator from the exhaust gases. And then you have typically a stoichiometric mixture of the warmed air and the fuel. And there is a combustion that happens in the furnace. And then there is heat transfer from the hot gases to the glass. And this heat transfer happens through different modes. So, of course, radiation is very dominant at those high temperatures. You also have convection at the surface of the glass. There is some amount of convection in the solid batch phase. And then there's a lot of internal convection due to the temperature gradients. And of course, you can have an additional source of electric heating from the bottom. So, and you have a lot of heat losses that happen in different parts of the furnace. So the net temperature of the glass bulk temperature would be a function of the throughput of glass as well as the net heat energy transfer to the glass and the material properties of the glass. Now, if you take a view of the energy balance, so considering that the energy that is introduced in the furnace through the combustion and the electric energy is 100%, and you are also recovering some energy from the exhaust gases. In addition to that, you can see that the final energy or heat that is carried in the glass is only about 40%. So you have significant losses either through the superstructure or through openings in the furnace, in the batch gas, in moisture, and so on. So there's a significant amount of heat losses. And these are also challenging to model, okay, because this is a fairly complex system, and all these heat losses, heat transfers, it's very difficult to derive the heat transfer coefficients from first principle standpoint. So this is a very challenging system to model from first principles. And hence, we are really advocating a more data-driven modeling framework, which also brings in some domain expertise and understanding of the physics, but leveraging data for actually building the prediction models and predictive capabilities. So in terms of modeling approaches, in general, there are different types of modeling approaches that you might use depending on your application. So in the controls community, typically linear control-oriented models are very commonly used just because they are computationally less expensive and they can easily be run online. And the problem, though, is that they are not very adaptable and also they are low fidelity, right? So if you want to get a very good prediction and with a linear model for such a complex process, it becomes challenging. On the other end, you have very detailed physics-based models like CFD or finite element models, which do capture the physics well, but they require a lot of effort to really set up and calibrate. They're usually calibrated only for certain steady state operating points, and they're not suitable for real-time applications. So what we are doing here is we are looking at how we can build a model to predict the performance of the furnace and then use that to optimize certain set points and also control the furnace in a more optimal manner so that you are able to get the best efficiency, throughput, as well as quality. So the approach we have taken here is more of a data-driven model using advances in AI and machine learning. So these are they are a domain-guided model. So we do bring in understanding of the process and physics, but they're mainly data-driven. But we do use the understanding of physics and the domain to make sure we have the right features in the model and also that the model's sensitivities are captured accurately. There is another area of research which is focused on physics-informed neural networks, which is having a neural network model that is consistent with the Navier-Stokes or the physical equations. Though this is still in research phase and these models are much more complex. So today, I think we would say that these type of models would still be state of the art in terms of application. And as you see, this is a bridge between the very simplified models and the most complex models. Now, in terms of the time series modeling techniques that we've used for forecasting and prediction, there is a whole array of models that we have evaluated in terms of increasing levels of complexity. So there are this linear models like ARIMA models, which are again data-driven models, statistical models. Then you have the conventional machine learning models like random forest, and then you have the neural networks where you can bring in time-lagged features. And then one level beyond is the recurrent neural networks and LSTM networks, which are more complex architectures. And then you have transformers and something called temporal fusion transformers for explainable forecasting. And really, these models are now getting closer to the ones that are used, for example, natural language processing and ChatGPT and so on. But the main difference here is that they are working on numerical data, and the problems here are definitely have their own unique challenges. So, so these are some of the methods that we have tried. And now going to the problem that we're trying to tackle here, the objective is to minimize the specific energy consumption in the melter. As I mentioned earlier, the melting is the most energy intensive part of the process. And it could be a combination of fuel and electric boosting energy. So it could be different types of sources. And the constraints are on the furnace bottom and crown temperatures. So these temperatures need to be maintained within prescribed limits. The crown temperature should not exceed a certain limit for a prolonged duration of time. Otherwise, it would lead to a very significant and fast degradation of the refractory in the crown. We also need to ensure that the O2 percentage or NOx in the flue gases is within prescribed limits. This is from the point of view of emissions as well as optimal combustion efficiency. And the glass quality parameters should also be within the acceptable limits from a customer acceptance standpoint. Now, you might have other types of formulations where you could leverage the same framework where you maximize the throughput while maintaining the same specific energy consumption, or you could try to maximize your quality and maintain same specific energy consumption and throughput and so on. So these constraints and objectives can be interchanged. And the approach that we use is a data-driven, deep recurrent neural network architecture. We of course also tried some of the other architectures, and we use these models along with a model predictive control and a real-time optimization strategy. And the reason we're using these complex models, again, as I mentioned, is because of the nature of the process. You have very long time delays and residence times, and also a lot of uncertainties in the process, complex nonlinear dynamics. And that makes it really challenging to model with just a very simple model. So this is just an example of one of the customers where we integrated data from different data sources. So it was a fairly complex data integration effort because there were different systems, for example, for actually monitoring the production. So in terms of the throughput and the production plan, then of course we had the furnace DCS, which was getting all the furnace process parameters like temperatures, pressures, flows. And then you had another system which was measuring the quality data, storing it in SAP, and then pushing it to the cloud, and then another one for the energy, calorific value, and energy measurements. So all these different data sources were then integrated, and there was a live data pipeline created, and then there was a furnace digital twin application running on the Microsoft Azure cloud, and this was able to predict the temperatures and also give optimized advisories, which were then passed on to the user interface so that it could be consumed by the end users. So this data integration is often very challenging. In ideal situation, you have all the data in a single historian like an OSI Pi, and you could pull that data and use it, use standard interfaces to the cloud. But sometimes the data is very much scattered, and there is a significant effort in the data consolidation and integration. Now, if you look at the overall furnace digital twin model, the kind of inputs that were used, so we've separated those into independent variables, dependent, and disturbances. So the independent variables typically are the fuel flow set points, the air to fuel ratio set points, and the electric boosting energy set points. And then the dependent ones are really the history of the key process parameters like the furnace pressures, furnace temperatures, and the crown bottom, etc., as well as O2 measurements. And then the disturbances are the glass throughput, because you have product changes and throughput changes, and the gas calorific value. The glass level is considered a disturbance here, and also the chemical composition of the glass and the moisture content and so on. So a lot of these are measured disturbances, so you could use those in your model for predicting your temperatures. And the output of this model is the furnace temperatures at the bottom and the crown. You could also get the specific energy consumption. And in case the quality parameters are measured frequently using an automatic inspection machine, then we could also use the same digital twin model for predicting the quality, rather the same framework for predicting the quality parameters. Now, these models require retraining because the furnace, as I mentioned earlier, is degrading over time. So you do have aging of the furnace, and you have refractory degradation, changes in the heat transfer coefficient. So we typically trigger a retraining of this model, and that retraining can be triggered periodically, or it can be triggered by a certain condition where the errors in the model exceed a certain threshold, or if there is a major change in the batch chemistry or in certain operating parameters, the user can also trigger a retraining of this model. Okay, so in terms of the modeling approach, the conventional ODE modeling approach is based on ordinary differential equations, which may be obtained from a partial differential equation, and then those are discretized, and you use system ID or parameter identification to obtain the parameters. But we've used more of the recurrent neural network, LSTM kind of architectures, and these are mainly artificial neural networks along with lags that are introduced mainly to capture the dynamics of the process and the delays in the process. Okay, this is some plots just showing representative validation. So we usually use a training data set for several months of data to train this model. And then we would have a separate test data set for blind testing. And for example, we look at transients to validate the dynamics of the model and check that it is capturing the dynamics accurately. And this is an example for the crown and bottom temperature, where the model was able to capture the dynamics for throughput changes. We would also look at sensitivity of the model and see that it makes physical sense. So we are able to achieve quite accurate multi-step forecasting of temperatures using these deep learning models. And so that is as far as the temperature is concerned. Now, in terms of the glass quality, sometimes you get these using automatic inspection machines, but often these are measured in the lab. And even the batch chemical composition data is recorded usually in the lab once a day. And the sparse data means that you often don't have enough data or the correlations are very weak, and using a neural network or deep learning model doesn't often work well. So we also use statistical approaches which are more robust. So you look at, for example, the bottom temperatures and quality parameter and try to look at the correlation and build a statistical model or use some statistical rules for the quality for handling the quality parameters. Now, in terms of the bottom temperature control, the strategy that we use is model predictive control. So what is done here is that the machine learning model or the AI digital twin model is used to forecast the temperature, as I showed 2 slides earlier. And this will give you the forecast over the next few hours. And then you have a set point, which is coming from your higher level real-time optimizer. And then your model predictive controller will iterate and pick the sequence of control inputs, which could be the fuel flow set points and air to fuel ratio set points that steers your forecasted temperature towards the set point, right? So it will try to minimize the error between your actual forecast temperature and the set point. And then based on that optimization, it will apply the inputs for the next time step. And these inputs, optimized inputs, would be shown as advisories on the UI screen. And I'll just show how that looks in a demo towards the end. So this kind of an MPC or advanced process control, it becomes important when you have a very slow process where the dynamics are very slow, the time lags are long, and you have a lot of uncertainties. So this kind of a framework is well suited to handling this kind of process over a standard PID controller. Now, if you look at the overall control hierarchy that we put together, so there is a module on top, which we call the quality energy control supervisory module, which is also the real-time optimization module. And what this does is it might use those statistical correlations and models, or it might use a more sophisticated model. But this will be used to actually minimize the specific energy while meeting the quality constraints or any other objectives. And it will provide the temperature set points for the furnace bottom temperatures. And those set points go to the model predictive controller. And then the model predictive controller runs this AI digital twin model and forecasts the temperature. And then it calculates the optimal set points in terms of the fuel and air to fuel ratios or the crown temperature set point, which then is fed into the DCS, right? And this could be a manual loop where the operator looks at the advisories and keys it in, or it could eventually be automated using an OPC UA link. So And you can see the different time scales. So this is running maybe once a day or several hours. This is maybe once an hour or half an hour. And this is running like almost real time. Now, this solution can be deployed on the cloud or for lower latency, we could also deploy this on-premise. Okay, so what are the expected outcomes? So with standard DCS controls, you usually see a lot of variation in the bottom temperature of the furnace. Could be of the order of even 20 to 30 degrees C in some cases where you have a lot of manual operation or a lot of uncertainties and variations in throughput and so on. With the MPC layer in the middle layer I showed you, you can reduce that variation in temperature significantly to plus or minus 3 degrees to 5 degrees or even tighter. And then using that top levels real-time optimization or supervisory module, you can adjust your set points at the higher level to reduce your energy consumption, right? So you have a so with the second, with MPC, you can tighten the distribution of your bottom temperatures. And then with the supervisory control, you can shift the mean so that you operate at lower mean temperatures, or you can adjust your set points so that you achieve your targets. And there is a potential for up to 3% fuel savings or 5% throughput increase while maintaining the quality, as we have seen in several trials. Now, this is just some results on one particular trial where we were firstly able to run this solution for several weeks uninterrupted on a real glass furnace, roughly 55 tons per day capacity, based on the digital twin advisories. So the operators were continuously following these advisories, and there was no disruption, very good feedback from plant operators. We've done this on at least 3 different installations or sites. And in this case, we observed about 2% reduction in specific energy and significant potential for savings. So you see that the orange ones are really the test AI-based operation, and the blue dots are manual. So we did observe a tighter spread and also potential to go significantly lower in terms of specific energy. And there was also a lower standard deviation of temperatures. We've baselined and compared this even against other APC solutions. And we were also able to keep the quality parameters within the limits. And another advantage of our solution is that we also do process anomaly detection. So you can use an AI model for anomaly detection to detect abnormal conditions like foaming, etc. So there's a lot of value benefits. So production improvement, fuel savings, defect reduction, emissions, automation, sensor fault detection, remote monitoring, and so on. So now what I'll do is I will move to a quick demo. So before that, I would just mention here that this is what the integrated solution looks like. So you have different data sources that can be integrated in the cloud or on-premise, and then you have a digital twin model that can forecast the temperatures, energy, defects, and also give set points to the operator for air rate to fuel ratio boosting and so on. And it can also raise alerts for process anomalies. And you can receive these alerts through email or SMS, and then the operator can act and follow these set points and then track the KPIs. Now we have done deployments for all these different applications that you see here, and successfully demonstrated the value. So I think we'll just move to the demo now, and I just want to show you an example of a dashboard. So this is a dashboard, main dashboard for the glass furnace application. What you see here is you will have an enterprise or a business group, and then you have a hierarchy here. So you can actually, this is an example of fiberglass plant. So you can actually look through the hierarchy. You have different parts of the process. So you have the batch, then you have the furnace. The furnace in turn has a melter and a throat. And then you also have the channels for Hertz bushings and HVAC and so on. And what you see here is that, of course, the user can change the time range and customize the time period that he or she wants to look at. You can look at the health of the overall process. You can look at alerts that are open, or alerts along with their status and the alert levels. And you can also upload a bunch of documents here and visualize some KPIs. Now, what you can see here on the top are some key KPIs like the specific energy, throughput, and so on. And you have a view of the different alerts here as well. Now, if you go to the alerts page, you can actually see all your process alerts along with the timestamp and the status. And the users can actually check the status, change the status of these alerts, assign somebody, add their comments, and so on. And also investigate these alerts in more detail, upload files, etc. Now, looking at the analytics and the forecast model. So we spoke about the forecast of the temperatures. So we have a separate page called the analytics page where you can actually look at the forecast trends. Now, this is an example of temperature forecast. So you can see that the actual temperature is shown in black, and the forecast temperature is the blue one, the blue circles. And you see that, so this is the history of the forecast, and then this is the forecast into the future. So, so the model, this is basically the output of that deep learning model that's running on the data, live data, and then it predicts over the next few hours horizon what the temperature would trend like, and it would also give you a confidence bound. So you can see the confidence bound also increases over time because the uncertainty is higher. So this model can, of course, be managed. We have our low code and no code approaches for building these models, pre-processing data, visualizing data, training these models, deploying them. And you can also look at the model history, retrain these models, and the whole MLOps around managing these models over the life cycle. So this is the forecast model. And then we also have an optimizer page where, so in the background, you have the forecast models running and you have the optimizer that is running. And the optimizer then uses that forecast to take decisions on how to adjust the set points. So this is a page that shows you some active and non-active set points. So the active set points are one where the operator needs to act at this point of time, and these keep getting refreshed, maybe depending on the process. It could be every 30 minutes or 60 minutes or so on. So in this case, what it's saying is that there is a current set point for the boosting electrodes, and you have some current value, and it is asking the user to adjust it by 1%. So the current set point is 67, and it is requesting a reduction of 1. And in this case, the current set point is 73, and the optimizer is requesting an increase of 6. Once the operator takes the action, then these set recommendations would become non-active because the operator has already acted on those, right? And as the operator acts on the set points, you can then track your temperatures using those time series plots, and you can also actually track your KPIs. So you could look at how it is impacting specific energy and so on over different windows of time. So this is just a glimpse of the application. Obviously, there's a lot more complexity and capabilities on this. So we also developed in the past a mobile interface for a similar application where we deployed an application with a mobile interface, and this was very helpful for users, especially during the pandemic period, to remotely monitor the furnace, in a very easy and convenient way. So I think with that, I will summarize now. So we believe that there is a great opportunity to improve the performance and the energy consumption in melting furnaces using the latest developments in AI and machine learning. And the data integration challenge always needs to be addressed first. So it's important that the data is well organized and that you can tap into those data sources and build a live data pipeline, and that you have the right quality of data in order to be able to build high quality models and optimization modules. The low frequency of the quality data is often a challenge. So there is a lot of push and move towards automatic inspection systems and vision systems. So that is really, those systems are getting more sophisticated, but we still see that there are challenges in terms of lab measurements being less frequent. And hopefully that will improve with more sophisticated systems. And also the vision and AI in the mix here. Finally, we believe that the maximum benefits can be realized only by integrating the voice of customer from all major stakeholders. So it is important to work closely with operations, planning, quality, maintenance, and the digital leadership so that the solution that is deployed meets the requirements of the end customer, and also that there is acceptance, and the change management aspect of it can be very tricky and challenging here. So it is important to have all these different levels and stakeholders and departments on the same page, and a strong push from the top level to make these solutions accepted and adopted by the industry. So I think with that, I would like to conclude the presentation, and we'll hand over to Tyler for a final poll question.
All
Thank
right.
you.
All right, fantastic, Prashant. Yeah, there is a poll based on what you saw. Would you be interested in to explore the use of AI ML-based digital twins for furnace performance optimization? Go ahead and get those votes in. Just a final tally to see if anybody's interested out there. Also, we did have some people directly message me, and they were looking for the copy of this recording, which I will have up on YouTube shortly after we close up shop here. So I will definitely send you out that link. Looks like we've got about half the room. And it's looking like they're split down the middle. Definitely or possibly. For those folks who voted possibly, we will definitely have Prashant or someone from his team reach out to you. So thank you for those polls. And like I said, some people sent me directly Prashant for the recording, but I'm looking at the chat for any questions anyone has for Prashant. Now would be the time to get those in, but I haven't seen anything else besides the asks for the recordings. If you folks have any questions for Prashant after the fact, you can reach out to the email that was attached to this invitation, and I will be sure to forward it on to you. But looks like that's it for questions, and we are past a quarter to the top of the hour, so we're a little over time here. So I'm going to say thank you again to our presenter, Prashant. I know these are, oh wait, we do have a message. Oh, it was a thank you. I thought that was a question. But Prashant, like I was saying, I know these are a lot to put together, so I really appreciate you presenting today. There was a lot of great takeaways, and it looks like the audience got a lot out of it as well. So thank you again. And to everyone else, we have Digital Manufacturing Talks every Thursday. Make sure you go to our website and check out upcoming events, and you can see them, what's all coming down the pipeline there, and you can register right there on that page. So be sure to check that out. And we hope to see you at a Digital Manufacturing Talk very soon. Thanks again, Prashant.